Greetings, friends. My name is John Gabriel, and this is a new calculus channel. And today I'm going to be going over Book 1 and Proposition 7. Since I've done the previous three, I figured that I'll just keep on doing the rest whenever I feel up to it and in the mood. So let's begin. Now, this proposition I think is a rather obvious one, and I don't know why Euclid bothered to include it. But I suppose that if he were to use this proposition later, which I don't think he does actually, then I would have seen some sense in it, but it's pretty obvious. The irony is that the way he does it is very obfuscated, since he does another proof by reducing to the absurd. Such proofs like this are very difficult to comprehend, and they start with an assumption, with an initial assumption that is actually incorrect, and then reach a conclusion which is truly absurd. So let's begin. Now, what I've done is I've placed these two triangles, which have the property that one of them, ACB, and the other ADB, have equal sides and rest on the same base. Now, the proof, as I've written it out here on the right-hand side, is much easier to understand than the one that Thomas Heath gives you here, okay? And the reason, for example, one can say, thus ADC is greater than DBC, is that we've already assumed that CAD is isosceles, and also the fact that ADC is equal to ACB plus DCB. Similarly, the next conclusion is also wrong, but it's based on the previous. It says that CBD is much greater than DCB. Also, again, from the fact that CBD is isosceles, and the fact that CDB is equal to BDA plus ADC. So these are concluded from the previous statement that ADC is greater than DCB. So finally, CB is equal to DB, and the angle CDB is also equal to the angle DCB, and this is where the problem comes up, okay? Because it was shown that CBD is greater than DCB. So, I mean, it can't be both greater and equal. Now, in just a very few simple lines, let me tell you what this proposition is saying. This proposition is telling you that you can't have two different isosceles triangles with these assumptions on the same side of the green base. Okay, in this case, I'm sorry, on the same side of this base, CD. It turns out that CD, if you don't look at it this way, then you miss this fact. So you have to consider the fact that CD is the base of these red and blue isosceles triangles. They're not actually isosceles, but you have to assume that because that's what you're given. So this infers that both the points C and D must be the same point if the assumption is to be true. Okay, so that's really all that rant is telling you. So it's totally unnecessary to have such a long and not easy to understand proof, by the way, especially when you're looking at this initially and you kind of stumble onto this thing here, the first one, which is thus ADC is greater than DCB. ADC, this angle, is greater than this one. Well, how do you reach that conclusion? There's only one way, from the fact that CAD is isosceles and the fact that ADC is equal to ACB plus DCB. Okay, so it gets quite involved. Now, I'm going to, I think, skip some of these propositions and go straight to the one that matters close to the end of Book 1, which is the theorem of Pythagoras in my next video. So I'll upload that in a separate video. And I'll leave you with these thoughts. I'll place a link to this applet so that you can study it in your own time. Now remember, you can move these points as you wish, and also this point. And of course, there are really two cases where you can have an isosceles triangle here, only two, when the points are like that, or when the points are like that, in which case they're not two different triangles, are they? They're the same triangle, and this side is actually equal to this side, so that's not that's not what is being asked in the proposition. So I'll leave it at that. My name is John Gabriel. This is New Calculus Channel. Till my next video, goodbye, friends.